Climate change is one of the top causes of soil degradation and is driving a loss of biomes with a process called desertification transition. Today, I would like to share with you how physics can help to identify and anticipate these kind of changes so that we can adapt or prevent them when possible. The desertification transition is a phase transition, just like when water turns to steam. And just like water to steam, the properties of the soil change drastically, which for soil means that it cannot support the same ecosystem as before. And again, just like water to steam, going back to the previous state is very hard and requires extra effort, beyond just lowering the temperature. There is a field of science that gives us insight into phase transitions. This is called statistical physics, and it helps us understand the common, universal features of transitions. One of these features is especially remarkable. When we approach the transition point, there is a lot of instability. This is a clear sign that we are approaching what in physics we call criticality. For climate change, we are indeed seeing this in local weather as extreme events are becoming disturbingly common. And this is also seen in plant growth. If we look at the Earth from satellites, we can spot this effect in the vegetation cover, which can become uneven or patchy with a very specific profile. This happens especially in semi-arid areas. These are the places where the deserts are actively advancing. However, the same patchiness can be seen in regions overused and made vulnerable by our human hand. Here is where the universal features of phase transitions come in. The patchiness profile is the same that is observed in phase transitions happening in magnets, polymers, and mathematically in the theory of graphs. Since this process has been studied in great detail in the last century, we are now very well equipped to recognize and anticipate what will come next in the desertification process. With these models, we can warn farmers and local governments about these changes years in advance, giving them time to prevent them. All this should remind us of the value of mixing ideas and methods from different scientific fields. At the same time, as theoretical scientists, we should welcome concrete applications of our knowledge because the solutions for saving endangered ecosystems may very well come from the physics of magnets and the mathematical theory of graphs.